All right, welcome back. Now we want to quickly look at unsupervised learning. So far, we have been looking at supervised learning, and I told us before that we have supervised and unsupervised learning under machine learning. Okay, so we have looked at some various algorithms under supervised learning, such as linear regression. We look at simple and multiple regression. Look at logistic regression. Look at support vector machine, decision tree, and so look at neural network. Those are very powerful tools, algorithms that we can use. But most importantly, we want to also quickly look at unsupervised learning, which means learning without supervision, no supervised agent. That is to say, there is no target variable involved. That is what it means. So it means there's no label. I think you still remember this definition. You can go back to read again, to check again. Uh, there is no label, there is no target variable involved. So in this supervised learning, we already have label. Whereas target variable, we already have our label set. Our target variable is already set. But under unsupervised learning, there's no supervision, there's no labeling, there's no target variable. So the algorithm, the model will help us to stratify and group our data set into different components, different groups, okay, different clusters. We call it clusters or segments, all right, so that we are not supervising it using label or target, right? But we are depending on the algorithm capacity to help us cluster it to different respective groups. Right. So that is in this case, there's nothing like accuracy, sensitivity, or recall, or specificity, or F1 score. No. We don't have that one under unsupervised learning. All right. It just the purpose of unsupervised learning is basically to cluster or to group. All right. I hope that should be very clear and understandable. Just to cluster or to group. That is the purpose. All right. So the first one we would like to look at it today is together is PCA, Principal Component Analysis. It's a dimensional reduction concept by which if you have a high dimensional data, for example, you have many variables or columns in your data set, sometimes you may not be able to make use of all of them appropriately because there are too many, especially when you have a big data. You may need to uh, uh, streamline your data into minimum variables so that you can be able to pass into the data. So this PCA is not only used for unsupervised learning, also used in supervised learning, but most importantly for feature extraction. If you want to extract features from your data, you have too many features. You don't know which one to extract, so you can use PCA to reduce the number of features, number one. Then, while you are still protecting or managing the minimum number of information that are required, you can still present a quality data using PCA. So, mean quality features. So PCA is commonly used in the field that deal with high dimensional data, such as speech recognition, signal processing, bioinformatics, and so on. It is also be used for data visualization, noise reduction, and class analysis. So it has multiple functions, and it works by considering the variance of each attribute, because the I attribute shows the good split between the classes, and hence it reduces the dimensionality. I generally try to find the lower dimensional surface to protect the high dimensional data. The importance of each component decreases when going from 1 to n, any number of PCs we have. It means that PC1 has the most important importance, and NPC will have the least importance, which means the last total number of PC we have. Okay, the last PC, or the total number of PC. So we want to look at a PCA. PCA is very simple and very straightforward. All right, and I want to show you how to use PCA, especially for feature extraction. Okay, it's very important for classification. When you are doing calculation, you might use for features for your data. So it's very powerful. So we are going to look, then we are going to look at also K clustering. K clustering is very powerful to cluster data. One of the most popular cluster algorithm is classifying the data set by dividing the sample into different K cluster for covariances. All right, the number of cluster must be specified in this algorithm as K. It is fast with fewer computations required with the linear complexity. So the data have no label, no target variable. So, but it's trying to help us cluster or group them to different inferior form. Then so you can see that here we have bunch of data combined together, trying to separate themselves into different groups. But they could not do that automatically. But after k-means is introduced, you can see them now separating themselves to different groups where they belong. So k-means will help us to group them to where each data belong. Okay, based on the distance measure. Using distance measure means most importantly uses Euclidean distance. All right. Okay, so there are other system techniques that are applied, but majorly the default distance that it uses is called Euclidean distance. Then we'll go further to what is called hierarchical clustering. Hierarchical clustering is very powerful. Okay, it can be used as an alternative for the partition clustering, as there is no requirement of pre-specifying the number of clusters to be created in this format. In the K clustering, you have to specify number of cluster, but here there's nothing like that. In this technique, the dataset is divided into cluster to create a tree-like structure, which is also called dendrogram. All right. I know you might have seen this kind of tree many times. It's common in bioinformatics as well. All right. So let's look at this clustering under the so then let's see what we are talking about quickly using how. All right. So we're going to let's clear the screen. All right, so I'm going to start by loading our library 31st for data manipulation. We load factor extra for clustering purpose, right, and cluster also in addition. So our data set will be, this data set is inbuilt. All right, you can just load it directly. Okay, when you load 31st, all right, you can load data set. Okay, and then also when you use factor extra, it's going to come with it. So you can just load this data set called US arrest. So you can check to see what it's all about. So we have US arrest. So let's see more about it. All right, it's showing us here violent crime rate by US state. This data set contains statistics in arrest per 100,000 residents for assault, murder, and rape in each of the 50 US states in 1973, also given in the percent of the population living in the urban areas. All right, so we have a data frame with 50 observations on 4 variables: murder, we have assault, we have urban pope, we have rape. All right, so it contains the data as in monograph. All right, so this is the data source. You can actually see the sample here. So, all right, so that is a US arrest. All right, you compare it to see how it operates actually, and you can see further. You can just this sample use, on how to use. Okay, but this does not give much information. All right, so let's just a few. Let's just do what is called glimpse. Let's glimpse as usual. All right, glimpse US arrest. Right, let's glimpse it. So let's see what is inside. All right, we have 50 rows, 4 columns: murder, assault, urban rape. 4 columns only. So we want to see how it's able to group this data. There's one more column that is not showing. All right, that is still there. All right, that is state, because it's not labeled. That state is not labeled. All right, so it's hidden, but it's part of the label. So we have only basic columns that are labeled showing here. All right, but if I see another column there called state, but the state is not labeled, so it's on label state, on label column, right? Maryland and the rest of them. So it's there. Colorado is, but it's not labeled. All right, but we will see later as we continue that that's on label state there. You can still have data set like that that you don't want to label, but it's there, but no label given to it. So it can also function the same way. All right, so the first thing I want to look at is, don't forget this particular section is divided into 3 parts. The first part calculates principal component analysis, and the second part calculates k-mean clustering, and the third part worked on the hierarchical clustering. All right, so let's first look at the PCA first. So we want to create PCA. It's very simple. We call the function pre-comp. We pass in our data set inside, then we scale to true. So let's create object called result and pass it to it. If you run this line of code now, our PCA is created automatically. So we can see let's also see the result of PCA by summarizing it. So this is the result of PCA. We have is 1, 2, 3, 4. So this particular data set now has been converted to PCA now. That's what it means. Okay. Now, how do you explain PCA? I start with explain what standard deviation of each, proportion of each variance, and cumulative proportion. Now we are having only 4 variables or columns, so it gives us only 4 PCA. It's not always like this actually. If you are having, for example, there's a data set called Soma. Let me show you this if it can help. Data Sona. All right. Oh, Sona not found. Let me see. Sona. A data set called Sona. Let me see whether it's uppercase. Let me try. Okay, it's uppercase, right? So I wanted to see this. Let's glimpse this first and see what is there. Sona, not to show you something I'm trying to say. All right, so Sona has look at what it has. 61 columns, okay, 208 rows. Now, this Soma it has a 60 features and one feature, one class. So this particular one now is a very powerful process. So I want to see now if you PCA, or I mean when you run PCA on this, it will reduce this particular feature to minimum. All right, let's try and see what I'm talking about. Don't forget that when we do this one, we have we're coming back to this very soon. Don't worry. Let's just run PCA. Let's say we pass we say PCA. Let's say PCA. Let's say PCA underscore Sona equals to let's call it pre-comp. Let's call it Sona. All right. So let's run this line. Okay. There's an error there because of this one. So let's minus this line 61, right? Let's work on that. Let's do like this. Comma minus 61. All right, minus 61. So what I'm trying to say, we're trying to subtract this column out of it because it's not a numbers column, not a numeric column. So to be giving error. So that's what I'm trying to do. So let's subtract it. Let's see if it works. All right, good. So it's compute. So let's summarize this PCA. Let's summarize and see what I'm talking about. Let's summarize and see the number of PCA we have. Summary PCA underscore Sona. All right, let's see the result. Look at result. How many PCA do we have total now? We have 60. So now from since PC now, what you have, you discover that only a few PC that make sense. Okay, let's look at what I'm talking about. Now from PC1 we have 74%. Okay, this one, this is 74%, 74.76%. This one 59.69%, 38%. So this is for each percentage of each PC, and this is cumulative of each of them. Okay, this cumulative proportion of PC1, PC2, PC3, PC4, PC5. So as a okay, this proportion of the standard deviation, this proportion of the variance, as you are moving down to the you see that the accumulation is increasing, to now by the time we got to PC 15, give us 93%. Okay, we go for that. Let's say 95% confidence interval. For example, now we have PC 17. Okay, 17 PCs give us 95% confidence interval. All right, that is where we have our CI. So it means that at this point, at this PC, or you can see maybe go further and go to maybe 95.18 and pick at 18, that will be 96%, but we want to stop at 95% CI. So at this point down upward, that is our PC we need to take. If you are using confidence CI, confidence about 35% confidence interval, you can pick from here downward to PC1. So it means from PC1 to PC17, that is meaningful PC. Others are meaningless. That's what it means. PC1 have the highest, okay, followed by PC2, followed by PC3, followed by PC4, like that. Okay, that is their what they call it, proportion of variance. So now the rest of, if you look at towards the end of the PC now, you say you need to have 0.00. Can you see? Because often it must be 100%, okay, or one it is 100%. Because it is 100%. But when you look at the proportion of each of them, can you see this one is nothing here. This is useless, nothing here. You can see all this one 0.000, 0.000, 0.000. Can see? So they are not making their proportion of variance is too small. All right, so they are not useful much. Okay, but if you go up, as you go up, you see that the PC it's becoming more bigger here, it's increasing here. So PC1 have the highest, followed by PC2 and 3. So the rest we can now pick a little more using our CI of 95% confidence interval. You might want to use 90% if you like. If your feature is not helping, if your distance is not helping, you can use just 90%. Okay, that will be fine. Or you want to use 95%, that's okay too. So 90% will give you how many PC? 12 PC. All right, 12 PC. That may be enough for you to classify or perform maybe neural network or SVM. That'd be very fine. So you just save it here, just pass the PC score here, right, and save it. Okay, let's say we want to save that here. You can just say right here, PC score. All right, now this is PC Sona now, not score. This is Sona, right? This Sona, for example, $X, right? Because there is always X, all right, beside it. All right, so let's say $X. So that is to generate the PC. Let's call it PC Sona. Let's call it PC Sona. All right. So that is just to test if you run to be safe. Okay, to be safe. So that is done. All right. So that is how to save your PC actually, as in your data. So let's go and look at the PC. Let's see how it looks like. Let's see the PC A. Where is it? PC A. Okay, this is it. Let's open it. Cut it here. PC1, PC2, can see them. So since you already know that only 4 PCs, only 12 PCs that give you 90% confidence interval, or you want to do 17 PCs for 95% confidence interval, then just from here, delete the rest. Just take only from here. Okay, the rest you delete. Okay, so this become your features you want to use for your classification. Then you can bring your target variable beside it. okay, which is the class. Can just be, I just put it beside it like this, so to classify. So that is how to extract features. So if it's got that maybe that one is not helping matter, you can also reduce further, can reduce to maybe to 10 until you have a better accuracy. So that is how you use a PCA as a feature extraction to classify. All right, so that is that for that. So let's continue with our calculation on a PCA, and I'm just to explain PCA just now before I quickly divert to this area. So let me just remove this. Okay, it's not needed. All right, let me just remove. So just to show you how we can do that. So all right, so let me clear the screen now so I can continue. So now we have done this. So we want to see the PC score. Let's see the head. Okay, now okay, something's wrong. Let's go back and recompute our this again. All right, let's show PC score. Okay, so now this is the one that is not showing there in the state Alabama, Alaska, Arizona. So you can see them. This is the state, but it doesn't have any heading, no label. Okay, so we have PC 1 to 4 here already. Okay, so but I want to use a PC to help us classify. We want to use a algorithm to classify them. K-means and also hierarchical clustering. So because you can first see the biplot first. Let's look at the biplot. Let's zoom out. The biplot is showing us here the 4 variables, this variable, this variable, this variable, this variable. So, but when you look at this very way, in urban pop, this 4 variable, the rape, the where you can say maybe where assault is more prevalent, murder is more prevalent, rape is more prevalent, is showing us in different region. All right, that is what it pointed to. That is a PC1 and 2 now we are showing now. So this is, you can see all the states around here. All right, so let's continue. So now this is just PCA, right? That's how PCA is. You can plot PCA scatter plot if you want. For example, using PC1 and PC2. All right, using G plots and plot PC1 on x-axis, PC2 on y-axis. Then you can plot and see the result, which is not bad. Okay, you can try that. So, but let's go ahead and see how we can do k-mean clustering in this regard. So we are going to first we use the fvis any cluster function to create a plot of the number of cluster versus the total within sum of square. So let's use this function first. We call our PC score. We call k-means to pass. This is a function we are going to use. This function comes from this particular factor extra. All right. So we are going to call the function, then passing our PC score into it. Then k-means method is called to WSS. So when we run this line, there are more that method you can use actually. This thing we want to find which cluster we to use. So we are going to use able method because it's 1, 2, 3, 4. This is able. So 4 clusters. So our cluster with the 4 following able techniques, right? The total sum square and number of cluster k is 4. This is how we discover our 4. Okay. So you need to run this first to discover how many cluster you want to, how many cluster. Okay, that is very important because that is not automatic. You have to find that out, and the only way to do that is to use this guy. Though there are many ways to find out cluster, there are many techniques that nowadays you can use to find the number of cluster. If you also see here we have 1, 2, 3, 4. 1, 2, 3, 4. This fourth one is called able method. Able method. Able. You look at your able. This is how your able looks like at the edge here. So this is able. The fourth one here is called able. So that is what we cleared. It took 4. So now perform k means clustering with k is equal to 4 now because our able is 4. All right. So now we create an object called kn, which is k means. Then we pass our PC score. We call the function here. Our center equals to 4 and n side equals to 25. So let's run this line of code. Run this line now. Plot the result of the final k-means now. Now we have done that. That is all. Now we now call this function to plot. Okay, we're passing our k-mean we have created here. We pass it here. right? The data is species score, right? We now print out. All right, let's print. You can see what you are printing. See. All right, so it helps us to arrange and group them, cluster them into different categories without any label, no target. Right, so if you check that the states that are closer in distance are grouped together, right? You can see that if you go to Google Map as well, Google Map, and check the US states and see their how close they are in the distances, you see that it helps cluster them accordingly. All right, we have Florida here, Michigan. You can see them how they are close together. If you look at how they are close together, look at how they are close together. So it will see that it will be correct, and you can confirm that also in Recurrent clustering as well. How they both use distances or Euclidean distances. All right, this is called PME clustering. All right. So let's go further and do Recurrent clustering now. The first thing we want to know to use the method to use to calculate our dissimilarity between clusters. That's the first thing we want to do. There are many methods to use, but let's follow this simple approach. Since we don't know beforehand which method will produce the best cluster, all right, we can write a short function to perform Recurrent clustering using several different methods. The cluster value is to 1, the stronger, okay? The closer this value is to 1, the stronger the cluster. So we have to let's create a linkage method here. We have m, let's create a function called m. So our factor c, we have this function, we have this method, both word complete, single, average, the method that we have under linkage method. So we pass into this function called this variable called m in form of vectors. Then you now say names m, c, average, c, word. So let's create this. All right, so we have done that. Then we want to create a function now, okay, to compute agglomerative coefficients so that we can find our this. So let's say create function ac, function s, we will pass Agnes function, pca score, method equal to x. We don't know s first, so we pass it later. So let's create the function. What I try to do, I want to find which function to use, okay, to compute our Recurrent cluster. That we want to find out the best method among these four methods we want to use. So let's see. So now let's apply m, calculate coefficient now. So now we have average give us 0.73, single give us 0.62, complete give us 0.83, and word give us 0.93. So this is highest. So this gives us 93.46. That is highest. So it means word will be the best method to use to separate our to cluster our algorithm. All right. All right. So now performing Recurrent clustering word using word now minimum variance. So because this method is word now. All right. The function just say h plus. This is the method to perform the h clustering, Recurrent clustering. This is the method. Then we pass our distance here, distance. Then we pass our PC score. Method equals to. So the method could be single, could be complete, could be average, could be word. So word.d is the method name. So that's why we use the word d. So word is the method. So we call it word.d here. So we run this line of code. All right. This run. Then we can now create what they call dendrogram. Dent. We create this for codent. We pass in function called a.dendrogram. We pass our hc that we have created with distance into it. All right. Let's run this line. Then we have installed a library called dent extend. Right? The purpose is that to able to color our record. If not, it will be displayed, but it will look very ugly, right? To not look beautiful. So we want to color it so that it can look more beautiful. So we call our dent. This is our dent here. Color label. Dent. We pass our dent here. Just creating a new dent here. Can create anything. Can use anything you want. Passing this. We have created. We pass it here. Case equal to 4. So we run this line. Now we can plot it now. If you plot it, it should be okay. Now this is it now. All right. If you zoom out, you can see. Now you see, it's a cluster. It's different. You can see We have 4 clustering here. But if you check something, something similar with what we saw in the K-means. Okay, let's look at it. Alabama, Louisiana, Georgia, Tennessee, Carolina, Mississippi, and the rest. So let's check again to confirm. Or let's save this. Let's just export, save as PDF. Let's call it a dendrogram. Let's call it dent. Let's go back and save this also as PDF. Let's call it a scatter, or let's call it cluster. So let's go and check and look at both of them. So we are actually done. Actually, we are done with this PCA clustering. So this is just the concept of unsupervised learning. That is all. We have many other clustering actually, but they follow the same approach. So don't be confused when they say unsupervised learning, supervised learning. No, don't be confused. There's nothing so special about it. So that is what it does is just to cluster. That's all. It's not for to give you usual performance metrics that you have in other ones. No. That is for supervised learning. But this one is just basically to cluster. That's all. Nothing else. All right? To group your data without any label. That's all. So let's check, compare the two and see what I'm talking about. So let's go to, we have dent and cluster. So this cluster now, this dent. Let's see. So let's it's not seeing clearly. Oh, no. It's not showing properly. So let's just have save it to something else. So let me just view it from here and show you what I'm talking about here. Let me view from here first. Okay, let's see here. So here we have Florida. Look at this. We have Georgia, Louisiana, Mississippi, Tennessee, Alabama, South Carolina, North Carolina, Arkansas. Look at them. Okay. Let's minimize. Let's go back and look at this. Let's zoom this. Don't forget those names: Georgia, Louisiana, Mississippi, Tennessee. They are together, so that you can be able to know. Look at it: Alabama, Louisiana, Georgia, Tennessee, North Carolina, Mississippi, North Carolina. You can see them. They are together. The same thing with this. Same thing with this. So which means that it's accurate using the distance measure. Okay, they're able to cluster them accurately. So that is what is called clustering. This is called dendrogram now. Okay, dendrogram. So you can run and test and see. If you have your data set you want to cluster that have no label, this is a good way to go. You can use this method to do that. So we'll be rounding up on this section now, and we'll be closing this particular course by ending it now. So because we have so far, if anything I need to add, maybe I will let us know. But for now, I think we have done justice to this particular course. We have covered several topics and different concepts has been covered so far. And I believe now you can work with how using data analysis, and especially in the area of data science. I think this is a good knowledge for you to acquire. And I believe that any question you have, you'll be able to post it, and you can also comment, you can rate, you can like if you find the subject meaningful and interesting, you can rate. I want to thank you for listening. I want to thank you for subscribing, and I hope to see you in another more interesting concept and topics in this group. So thank you so much. I'll see you next time. Meanwhile, the data used in this course will be made available, and the necessary tool that you need will be also be supplied. Thank you.